Alright everyone, today we're going to be taking a look at the Ivy Bridge processor and Ivy Bridge platform that currently powers the Retina Display MacBook Pro as well as the other 2012 MacBooks. And to begin, we're going to look at some big differences between Ivy Bridge and Sandy Bridge, which was the previous platform. The first difference that took place in Ivy Bridge is that it's currently built on a 22 nanometer process, whereas Sandy Bridge is built on a 32 nanometer process. Now what this means is that the individual transistors that make up the CPUs are smaller in Ivy Bridge by a factor of 10 nanometers versus the old Sandy Bridge processors. What that means is that everything being equal, in terms of thermal characteristics, input voltage, and cooling systems, a 22 nanometer processor should always run cooler than the 32 nanometer Sandy Bridge part. What this means is that you can put in less voltage into the CPU, less battery power into the cooling fans, and therefore get a longer battery life coming off a 22 nanometer processor. So that's the first really big change that happened when they switched CPUs from Sandy Bridge to Ivy Bridge. The next thing that's closely related to process manufacturing is the thermal design power, or TDP, of the processor. Now, TDP is a measure of measuring the cooling, or how much cooling you're going to have to put into the chip. So what this means is that Intel guarantees the manufacturers that if it dissipates a certain amount of heat, the CPU will operate as intended. So let's take this into a more real example. If your processor has a 35 watt TDP, that means the manufacturer has to ensure that it can dissipate 35 watts of heat. If you go over that thermal limit, and if you don't dissipate 35 watts of heat, the processor is not going to be able to run at full speed. So the lower the TDP, the less design effort that's required to cool the chip down to make sure that you operate as fast as possible. And when looking at the various TDPs, the big processors like the 15-inch MacBooks, they generally have a 35 watt TDP involved. So that means you have to cool it down by 35 watts or else the processor is going to throttle down. And with the MacBook Air, those are ultra low voltage CPUs, and that's also why that the clock speeds are pretty low. The MacBook Air has 17 watt TDP, so that means that inherently the MacBook Air processors are going to run a lot cooler. Another thing in terms of talking about voltages, the current line of MacBooks and MacBook Pros use DDR3 low voltage memory. So before, on the previous generation, DDR3 would run at 1.5 volts and DDR3L runs at 1.35 volts. So there's a difference of 0.15 voltage between the two memory, and this allows the current generation to again get more battery life out of the laptops. And they also tweaked a lot of architectural changes to the chip itself. Specifically, to pull more performance in Ivy Bridge versus Sandy Bridge, they kind of re-architectured the way that they did hyperthreading. Now, hyperthreading is the component that allows a single processor to split up its instruction queues and instruction buffers and make a 4-processor or 4-core CPU look like it's 8 cores to the operating system. So let me explain how this works. Most programs these days are operated on the concept of threads. So what happens is that a program will execute multiple threads, and a thread is like separate instructions. So a program can send out multiple instructions at the same time. And in the best case scenario for hyperthreading, the program will, say for instance, issue 4 threads. And those 4 threads will be copied into instruction buffers or instruction queues. and each buffer will cache the instructions coming off of the program, and when the execution resources are free, then those buffers will flush out and send all the instruction threads through the execution units, and then program execution will run faster. So you always have a full pipeline. You always have all the execution units full of program instruction and program code, and that's what makes virtual CPUs more desirable. Now, in the case of Sandy Bridge hyperthreading, what we have is that, let's say we have a program that issues only one thread. And there are many single-threaded applications out there, just because it's kind of a pain in the ass to create multiple threaded programs. It takes extra effort to create programs that are properly multi-threaded. So let's say you have a single-threaded program. What it'll do in Sandy Bridge is that the program will send out its instruction thread into a buffer, and it's only utilizing, say, one buffer out of four. So you're going to have 3 empty buffers and 1 full buffer, and the program's instructions will be sent through and go into the execution units. So basically, you're wasting silicon space and you're wasting buffers because it's not a multi-threaded program. With Ivy Bridge, they set it up so that the instruction queues are dynamically controlled. So what can happen is you can have a program that sends down a single thread, and instructions from that single thread can be split up between the 4 buffers. And in actuality, there are way more than 4 buffers. I think there's something like 20 or 30 buffers for each core, or something like that. But let's just say that there are 4 buffers. So a single thread can be split up between the buffers, keep everything full, and keep execution time going along smoothly. So that's the first thing that they did in implementing hyperthreading. Another thing that they did is that they increased the throughput of the floating point and integer dividers as opposed to Sandy Bridge. So when you're doing floating point operations, they have twice the throughput as Sandy Bridge, which means that floating point calculations should be able to go through more quickly coming off of the FPU. Another thing that they tweaked on Ivy Bridge is that there are more speed steps or more levels of processor speed that's selectable to you. Now on Sandy Bridge, you had 3 speed steps available to you. First, you have something called LFM mode, and that's the slowest that the CPU is going to clock itself at. Think of it as power saving mode, when it's not doing anything, when it's sitting idle. Above that, you have nominal mode, and that allows the CPU to do normal work, and that gives you a good base clock of, say, 2.0 gigahertz or 2.2 gigahertz. That's nominal mode when it's doing some type of calculations going through it. And then, of course, you have turbo boost mode, and that's when the processor overclocks itself, when it can shut down a core or two and really put all of its processing resources to 2 cores as opposed to 4, and it'll allow it to do an overclock. So what happened now is that there are more speed steps to the turbo clocking or to the turbo boosting available to Ivy Bridge. And what that means is that you have more discrete steps or more discrete voltages available to the chip, so it can more dynamically control the voltage and electricity going through the chip. Another thing that Ivy Bridge has is something called power-aware interrupts routing. And what that basically means is that, let's say you have 2 out of 4 cores active. What it does is that it looks at the instruction stream and says, which cores should I send this to that are already active? So it's only going to send instructions to the active cores instead of routing it to sleeping cores or inactive cores. And if you don't have to wake up inactive cores and just keep it through cores that are currently active, you're going to save some energy. So that's interrupt routing in Ivy Bridge. And for the final set of tweaks, they kind of redid the processor or the graphics side of the processor. And what they did is that the HD 4000 graphics in Ivy Bridge has 16 execution units versus 12 execution units available in Sandy Bridge, and the HD 4000 supports DirectX 11. So that's why you're getting a bit of a better performance on the gaming side when using HD 4000. And another thing too is that there are twice as many instructions per clock for each execution unit as opposed to Sandy Bridge. So when you add up the differences, if we're just looking at the CPU side of things, you're going to get about a 4 to 6% increase in performance for Ivy Bridge at the same clock as Sandy Bridge. So in other words, a 2.2 gigahertz Ivy Bridge will operate 4 to 6% faster than a 2.2 gigahertz Sandy Bridge, and that's just because of some of the improvements such as hyperthreading and the speed stepping to it. And mostly Ivy Bridge is designed to save power and make sure that your processor stays cool. Whereas the next jump in Intel architecture is going to be Haswell, and I think that's going to come out in mid 2013. And Haswell is going to have significant improvements to the processor architecture, so you can get a faster speed difference between Ivy Bridge and Haswell. So that's the next great thing to be looking out forward to.